Okay, can everyone hear me?
Yes.
Good. And everybody sees my screen, I think, right? Well,
Yes.
great. Welcome back to one of our last Monday classes. Thank you, Emma, for pointing out that next Wednesday is not a class day. We only have 4 classes left, not 5, as my email last night said. I apologize for that. I'm always making those kinds of mistakes, but I count on you guys to keep me honest on all that. So what we're going to do is we were going to have a review on next Wednesday, but we'll have that review on next Monday. Next Monday, I'll go through. I'll give some kind of overview and review of the course. That doesn't affect our Wednesday class this week and our Friday class this week, which I hope you'll enjoy. I did send out some materials for you guys to prepare on all that. You also have 2 assignments that are only extra credit. They cannot hurt you. So if you're feeling overwhelmed, then blow one of them off or blow both of them off. They will not hurt you if you don't do them. They're just an opportunity for you guys. One should be pretty fun and helpful, and there's some money behind it too. That's the Safe Schools Challenge, and then the other one is a homework assignment. Now, just so you know, that homework assignment would have been a good test question. It would have been a difficult and tough and devilish test question, but it would have made a lot of sense from a professor's perspective that be a test question. And so what I thought I'd do is give it to you open book, across a whole week, and give it to you for extra credit. And so that's sort of the way you can look at it. It will reinforce a lot of the stuff that we've been looking at in chapter 3, and also the specific pieces of chapter 4 that we talked about the last couple times, and that we'll wrap up today. Obviously, I can't go through all of chapter 4. All of chapter 4 actually is, in my opinion, is a real big chunk of an entire course that you guys will see in Signals and Systems. And so I think it's really good actually you have this big picture, this introduction to what's going on in that, and especially the connection to your circuits class that you'll end up taking. And usually what happens is people will take the circuits class and they'll learn half of the puzzle, and then they'll take their Signals and Systems class and they'll learn the other half of the puzzle, but maybe they don't see that it's the same puzzle. There was that whole story about blind men touching pieces of an elephant, and each walking away with a very, very different view of what the elephant was, because one touched the trunk, one touched the side of it, one touched the feet, and so they all got a correct but different picture of what that elephant was. And so one of the things that I hope you'll do when you take your circuits course and when you take your signals and systems course is go back to these lectures, go back to these slides and see again, remind yourself how what I'm trying to do is to pull everything together for you, to give you a simpler picture of the whole, a simpler and cleaner picture of the whole, which I think all too often gets shortchanged in the way we do these courses. So let's go back and do a little bit of review. We've been looking at this particular filter. Again, we know this as a low pass filter, and we know this because of the behavior of the capacitor. At high frequencies, the capacitor will take a signal and shunt it, short it out all the way to ground, and so only the low and then the low frequencies get blocked, and they don't even see this huge impedance that this guy is. It all goes through the resistor, and we used very nicely. We used our complex impedances to derive the frequency dependence, and that's something we call the transfer function. And now what we're doing here is we are going back and looking at the time dependence, and the time dependence gives you a differential equation. And that scares a lot of you because you're not supposed to have ever seen a differential equation before, and boy, isn't this unfair that I'm presenting it. But I'm not testing you on it, and I fervently believe that a gentle introduction to this is a great way to get some exposure to it, so that and it really will give you a step up when you in the next couple semesters when you do see differential equations. And the point of this is it's not hard. The form of this equation comes out just real naturally from the Kirchhoff's current law and the rules of the road for the resistor and the capacitor, and it just happens that it is an equation that has a derivative in it, and an equation that has a derivative or more in it is a differential equation. So there you have it. And here is our differential equation. And the first thing you learn about these differential equations is to ignore, for now, this input or this forcing term. And if we had one more class, one more Monday, I would go back and I would show you the beginnings of how to bring that back into the equation. But we're not going to do that, and it probably would have been a failed experiment anyway. You probably would have just shaken your head. It might have been just a one step too far. But so just know that that's hanging out there. That somebody somewhere down the line we're going to have to fix that. And when you see it, you'll just go aha. And I'll just tell you that in my opinion, the mathematicians fixing that, they don't do as clean and elegant a job as the signals and systems course will when you see that. So first thing we do is we kill the time derivative. We get rid of that, and then what we have is we have no forcing term, an unforced differential equation. And look, this differential equation is 2 lines long. It's 2 terms long, right? It's a dV/dt, and it's another term that's proportional to this. And last time what we did was we did the formal way of solving a differential equation, which is we assume a form for it, and we guess a form for it, and the guess always works out right when a professor is doing it, because they've had the benefit of working offline and getting that answer somehow. This is such a common differential equation that most people who take this is one of the very first differential equations that you'll look at and do. I want to talk a little bit about this today. A couple of things. One is, so let's let me so let's see the differential equation. There we go. The differential equation is dv dt plus or minus plus 1 over RC times V equals 0. And one thing to note is I can write this as dv dt plus a V over a tau, where tau is a time constant. And so the RC is equal to tau, and that's consistent with the phrase the RT time constant. One of the reasons I'm doing this is I want to point out the units on this. The units here are volts divided by seconds, and the units here are also volts, and the units here are seconds. So I have volts divided by seconds because of the derivative, and naturally because of the physics, I've got volts over seconds because of the RC time constant. So that's really nice to see, and I just wanted to point that out, that units help you sort of explore and talk a little bit and get you in the sync of things. And so the next thing I want to kind of point out about this is there's actually another way of solving this equation. And so if I multiply through by dt, and that should shock you, that should kind of rock your world a little bit, because mathematicians hate that because it's very sloppy, but it's also very convenient to be able to do. A change in voltage divided by a change in the time. Well, gee, I'll just multiply through by that change in time, and that's what I get. And so then what I can do is I can integrate both sides. Integrate this guy with respect to a voltage. So I'll have the voltage as a function of time. Let me think. Oh, did I mess this up?
I don't think you did. Sure.
Wait a minute. This always happens when I do something that I shouldn't be doing. Oh, I know what I did wrong. I'm so sorry. I almost did something right, but I didn't quite do it. Let's see if I can undo some of this stuff. Sorry about this. So I want to multiply through by dt, and I want to get all my voltages on one side. That's the mistake that I did, Rashik. Sorry about that. I forgot to do that. And so now what I can do is I can integrate both sides. And the right-hand side is my minus t over RC, my time constant. And this guy here is a hard integral to do. It gives you the ln, the natural log of the voltage, which is equal to minus T over RC. And then from there, I get V is equal to V naught E to the minus T over RC. And I'm being really sloppy with my use of my limits of integration here. So I'm being really sloppy about that, just because I want to show you big picture that you actually can formally integrate this differential equation. You can't you don't always get to do that, only with first order derivatives and things like that, but you really can do that here. And now you see exactly where, for a positive resistor and a positive capacitor, where the minus sign comes from. Okay, so this gives you a little bit more confidence in your guess. We can in fact imagine deriving this answer, but that's very rare, and it's almost misleading, because in general you need to guess your way through the answer for a differential equation. It just so happens that this is of such simple form that we can do this. Now this is this equation is, and I want to just make a digression on this a little bit. This equation is really general, and if you think about, what's going on with the COVID-19 pandemic, right? You see in the early stages of the disease, you see an exponential rise, an exponential growth in this, in the number of cases in the early stages of this disease. And this rising exponential comes exactly from this differential equation, except with a positive sign here. So this equation is so applicable in so many different fields that now you can start to understand some of the mathematics behind a pandemic, behind a disease piece of the puzzle. And so the time constant here, dictates how fast, how sharp this rises, how fast, how sharp this decay is for our system. And I'll let you think a little bit about, remember we talked about stable and unstable, stability and instability, and I'll let you kind of chew on that a little bit, and why the resistor and capacitor is so inherently stable, and why a life reproduction of a virus or reproduction of a life form may be unstable until it runs out of resources. I don't know, when I was in high school in biology class, we had this little petri dish filled with fruit flies, and every day we would count the fruit flies and how many there were in there. And in the early days, you saw this rise in exponential, but then the resources of the petri dish went over, and the whole population collapsed and went to zero. And so to describe that second half of that data, we need more terms on our differential equation, and each term has an interpretation of that. Okay, so that's a little bit more on. That's a little bit more on our guess, a little bit more on our differential equation. To remind you, this is the better way of solving the differential equation, which is guessing the solution and substituting it in. So to do that, we need a form for V, which is V naught e to the minus alpha t. And when we need to have something, we put into this dv dt term. And so what we have to do is we have to take the derivative, d by dt of this, and the derivative of the exponent is the same function multiplied by what's upstairs in the argument. And so I have dv dt is equal to minus alpha v naught e to the minus alpha t. Very, very, very important to note that I have this functional dependence and this functional dependence, and they are exactly the same. They are exactly the same, which means when I multiply through by e to the positive alpha t, I cancel all the time dependence from my left-hand side to my right-hand side. So there's no time dependence left after I divide out by the e to the minus alpha t. And so this equality will hold. This equality will hold for all time. And that is the definition of solving a differential equation. So how do you know you guess right? Well, the equality will work for all values of time and not just particular, well-chosen, convenient pieces of time, instances of time. So this piece of the puzzle here is a real important conceptual piece for solving a differential equation. Is when you get to divide out this term and this term, that's when you jump up and down and give yourself a real loud cheer. That's the feel of success for solving this differential equation. Okay, so here's my physical picture of the e to the minus t over RC. The initial conditions comes in and charges up this capacitor. Charges up the capacitor. The role of the initial condition is to put charge on this capacitor. And then once the switch is thrown, the charge migrates through the resistor and drops through the resistor. So originally, when we have lots and lots of charge, we have a very high voltage drop across the resistor, but we only have a fixed amount of charge. And so over time, we get less and less and less of a voltage drop until we run out altogether of all the charge, and then the voltage is relaxed down to zero. So this is the physical picture of charging. The initial condition charges this capacitor, and then the action of the current flow depletes that charge on the capacitor and drizzles down to zero. And there's a great mental picture here that I'll push a bit, just because it's fun to think about. You've organized, by charging this capacitor, you've organized where your charge is. And so that's very much like having a very, very well organized, let's say a bucket of Lego, the little toys that I used to play with as a kid, and my children played with when they were young. And so we'd put all the Lego. We'd start on a Saturday morning. We'd have all the Lego in this basket, and then over time, over that morning, as my kids were playing, that Lego got everywhere. And so we had to do work to pull all the Lego back together into the basket. And so this organization of charge here is like the pristine organization of Lego in a basket. And the dribbling out of this is an increase in disorder. And there's a word that you may have learned, but probably not mathematically yet, and that's entropy. And so the low entropy state here, the highly organized state here, devolves or just degrades to just random heat and thermal energy that has no order whatsoever, or has very high entropy states. So there's a nice little thermodynamic piece of the puzzle that goes here as well. And again, how do we charge this? How do we get that initial condition? Well, it's the role of the delta function that goes in and charges up that capacitor. It charges up that capacitor. And so the output of this delta function response we've been calling the impulse response. And notice that we've described this as little h of t, and we've done that for a while now. And so the delta function response is this v naught e to the minus t over rc, and that allows us to start our class today after a little bit of review and context setting. So here's our h of t. And actually what I want to do on this is I want to put in a step function in there. And what that step function does is it takes my exponent and cuts off the stuff that occurred before 0. So now what I want to do, just for fun, just because I can, and then I'll explain all this later on, I want to consider an integral that is this e to the minus t over rc, u of t, e to the minus omega, sorry, minus j omega t dt. Okay? Just for grins, that's what I want to do. And I'll go back and I'll talk about why we want to do it and what it means, and in particular, what it means to have minus infinity to infinity and why we want to do that. But let me just work the math for a second. So the u of t allows me to change my limits of integration from minus infinity to 0 to infinity. Makes the problem a lot nicer. And then I'm using this very, very powerful rule of exponents to combine the t over rc with the j omega. So now I've just got one term in my exponent. And if I squint my eyes, this is just everything in here is just one piece of the puzzle with respect to time. It's all constant with respect to time. And so if I integrate this, I get 1 over 1 minus r 1 over rc plus j omega. And I have to evaluate that at t at minus infinity minus e at 0, and should be a minus sign here. And so this guy goes to 0, this guy goes to 1. So this is equal to 1 over rc plus I omega. So I can write this as rc over 1 plus I omega rc. And then if I or j omega rc. And this is equal to V out over IN over C. So if I change this to if I change this to, so this is equal to RC times I out over I in. This is little details that I don't want you to worry too much about. But what this tells us is exactly I out over I in is equal to 1 over 1 plus j omega RC, which is what we called h of omega. And there's no accident, it's no accident that we're using the same letter, little h of t and capital H of omega. So this is the transfer function that we got before. So the delta function response is connected to the transfer function, and that's absolutely not an accident. That is absolutely not an accident. Okay? And that's sort of the punchline. That is absolutely the punchline of what we've been doing for the entire course. The very first thing we did with the course was we said, hey, I can write a function in the time domain, or I can write a function as a function of frequency, right? I had my sinusoids, and I could write my sinusoid I could plot my sinusoid as time, or I could plot my sinusoid as frequency. And then we noticed that songs and music have different frequencies that come into place at different times. And so we could write a song, we could play a song as a series of musical notes, as a series of sines and cosines. And so we'd have a changing sound as a function of time, but we could also, because they were all connected to sinusoids, we could also plot at any instant of time what the music was in the frequency space. And so now our punchline for this is that h of t e to the minus j omega t dt goes to h of omega. And now we can start looking at what we're doing here. Now we can start to look at what we're doing here. And by the way, this is in chapter 4, section 4.8 of Johnson. Okay, just to tie you to where we are in the book. Although he does it a little bit more generally than what I'm doing, and I'll get there in just a couple of minutes. So what are we doing here? Well, we've got this piece that we stuck in to our integral, and this is called a kernel, and it's the complex exponential of our favorite function. So this piece here, this function here, introduces sines and cosines into the problem. Notice how these guys are arrayed. So when I integrate over all time from minus infinity to infinity, I get rid of the time part. This is a definite integral with respect to time. The time goes away, and what I'm left with is the overlap, or the collision, the averaged collision, or the integrated collision of the information in h of t with all the different sines and cosines, with an arbitrary frequency sine and cosine that are in there. I haven't lost any information whatsoever. What I can do is go back and I can get h of t, And I'm lying to you just a little bit. There's a constant in front of that. And various books do various things, but the constant has to do with 2 pi somewhere in the problem, because omega is 2 pi times the frequency. But basically what I can do is I can go back and forth between h of t and h of omega. And this is called the Fourier transform. And what it allows us to do, is move very gracefully between the time domain and the frequency domain. Like being able to express rigorously and carefully and in an incredibly useful manner the same amount of information, either in the time domain or the frequency domain, either as a function of time or a function of frequency. And the nature of this integral, allows us to understand where that comes from. We are moving from one representation, in this case, the frequency representation. We're integrating from omega equals minus infinity to omega equals infinity. So we're including all the information across every single frequency component we can think of. We're not leaving any frequency component out. But it's also a definite integral. So when we get to the other side of this integration, there is no omega and there's no t when we get to the other side of that integration. And then, and so the wonderful way this j omega t works, is we swap out gracefully an omega for a t and a t for an omega. And then you notice, lastly, that the sign of that kernel, the sign of that exponent, is changed. When I go from the Fourier transform to the inverse Fourier transform. Okay? So in the book, they talk about it more generally. So f of omega is equal to minus infinity over infinity of f of t, e to the minus j omega t dt. And f of t is equal to, I'll put 1 over 2 pi here, minus infinity to infinity of f of omega e to the positive j omega t d omega. T equal omega equal. And so these are Fourier transform pairs. So sorry for the vocabulary. It's so distracting that I'm just giving you what people call it. It's the Fourier transform pairs, and allows us to move very, very nicely between these two pieces, between these two representations. I will say one final thing about this. Well, I'll say one thing. All I can point out to you is that this is very, very, very useful, but it's also something we've wanted to do from day one. We've wanted to have a rock solid way of moving from the time domain to the frequency domain, moving from writing a signal as a function of time to writing a signal as a function of frequency. So time domain, t, f of t, frequency domain, exactly the same amount of information, except drawn in the on an omega. We also need the square root of -1 to be able to do that. So that's an important piece of the puzzle. F of omega will in general be complex, as we've seen from the F of omega will in generally be complex. And then I'll close out the course with one piece to tie into one of our Wednesday and Friday lectures, which is digital computing, discrete time signal Fourier transform. To be able to do this digitally by brute force,